Hi, good morning, everyone. This is Amrit Gunasekara from the California Department of Food and Agriculture, and I'm going to be moderating this webinar titled California and the International Community, Looking at Soil as a Climate-Smart Agriculture Strategy. Today is World Soils Day, and we're very excited to be part of this incredibly valuable day, talking about something that sometimes we underappreciate. We have a great lineup of partners. We are looking at partnering through this webinar with obviously the California Department of Food and Agriculture hosting it, with the Food and Ag Organization, the USDA, the International Maize and Wheat Improvement Center, University of California Cooperative Extension, and Genera Cycle. We're going to get started today with some introductory remarks from the California Department of Food and Agriculture Deputy Secretary, Ms. Jenny Lester Moffitt, and she's going to start us off with welcoming us and giving us some introductory remarks.
Hi, good morning, good afternoon to all of you on the call. At a soil conference in May, Christiana Figueres, former Executive Secretary at the United Nations Framework Convention on Climate Change and the Chief Negotiator for the Paris Climate Agreement, very aptly said, carbon is like real estate. It's all about location. Carbon is a frenemy. It's either a friend or an enemy based on its location. Carbon in soil is a friend. Carbon in air is an enemy. We need to change the location of carbon. We need a huge conveyor belt to move carbon back into the soil. Now, she also recognized that it's not that easy. Soil is not a technology, it is a system. It's a system of building microbial activity to improve productivity, sequester carbon, and create water infiltration to help get us through drought. Understanding that system and adopting systems-based practices takes knowledge, research, resources, and leadership. And we are excited that this year, for the first time, California is participating in this World Soils Day today and throughout the rest of this week with a week-long series of events. Our theme, Healthy Soils, Healthy Lives, in recognition of the fact that California's soils help feed the world, conserve water, improve air quality, and fight climate change. In California, we launched the Healthy Soils Initiative in 2015 to do just that. The Healthy Soils Initiative is an integrated approach to support practices that build soils. And it is part of our state's ambitious climate goals, carbon sequestration in the working lands. Today, we will hear from many speakers on soils and their role of mitigating climate change and building a food system that is more resilient to climate change. And that's important because there's 3 times more carbon in the soils than in atmosphere. And carbon in soils is all about planetary security. Food security, water security, home security through migration, creation of jobs. Through soils, we can improve and secure livelihoods of the global population, because healthy soils does mean healthy lives. Thank you, and I look forward to hearing the presenters today and the conversation, not only today, but for the future to come.
Thank you, Deputy Secretary Moffitt, for those welcome remarks. We're going to move on to panel 1. And panel 1 is titled, What are Healthy Soils? A closer look at the composition and benefits of building soil organic matter. And for this panel, we're going to hear from Dr. Geetika Joshi. She's a supervising senior environmental scientist who manages several climate change incentive programs here at the California Department of Food and Agriculture. She has a PhD from the University of California, Davis in soils and biogeochemistry, and we'll now hear from Dr. Joshi.
Thank you. Good morning, everyone. And once again, thank you so much for joining us today across the world and across time zones to celebrate World Soils Day together. And I will be talking about taking a closer look at soils and what soils really are, how are they formed, what is soil organic matter, and why is it so important? And as I set this up, we will be hearing from other speakers as well who will talk about all of the different aspects of soil health that we should be thinking about. For many of you joining us today, some of my slides might be a refresher in soil science if you've taken those types of courses or doing that kind of work in the past. And hopefully for some of you, this will be information that helps you learn and understand soils better. So let's take a closer look at what soil is formed of. So this figure kind of shows us all of these different levels of aggregation in soil. And before we even look at that, soil is a really complex three-dimensional environment. And it's formed of mineral particles of different sizes. And interspersed between these mineral particles are different types of organic fractions or organic matter. And as they're arranged together in a three-dimensional space, there are pores, convoluting pores, and waves, and sort of tube-like structures that are interspersed throughout the soil profile, through which soil water as well as the oxygen or the soil air can flow through. And all of this is really important for sustaining life within the soil, the small organisms that live within these soil pores, as well as creating an environment that can support plant growth, which, as we all know, is so important for our food production. And there are different stages of aggregates that are formed in soil, all thanks to organic matter in the soil. And primarily, the sticking together of soil at different size ranges forms aggregates of different sizes, as are shown in this figure. And all of the mineral particles that are held together by glues and gums that are either secreted by microorganisms that live in the soil through the different types of biochemicals that are present in their cell membranes or in their excretions or exudations, as well as plant exudates that are secreted by roots that all hold together these different soil particles and organic matter in different size aggregates. And aggregation is a really important aspect of soil health and keeping that soil healthy, porous, and thriving. So with that, let's take a closer look at some of the soil particles, especially the mineral soil fraction. As for all of the soils of the world, except for organic soils, these mineral particles form the skeleton structure of the soil itself. So these particles are composed of mineral particles of different sizes, and they are classified according to their sizes. The three main primary fractions are called sand, silt, and clay, the sand particles being the largest, the silt of the next size range, and clay the smallest particles. The size ranges are shown here in this table. So clay particles are less than 2 micrometers, silt particles between 2 micrometers to 0.05 millimeters, and then sand particles are larger than the silt particles. Additionally, the way we classify soils, especially in our USDA classification system, sand or particles can also have some qualifiers, such as very fine, fine, medium, coarse, and so on. And all of these are quantitative numbers. And as you can see, each one of these particle sizes and qualifiers correlate with specific particle sizes. They really help us as soil scientists to classify the type of soils we have by looking at these particle sizes. The particle sizes, of course, have an important impact on the kind of pores and pore sizes that are formed within that overall soil structure, and therefore how much space there is for organic matter to complex with the soil, for microbes to live and thrive there, and so on. So with that, let's take a look at these sand, silt, and clay particles. So we do have a chemical structure here showing an aluminosilicate or a silicate particle, which is the primary composition of sand. Sand, as I mentioned earlier, those are the largest particles, the loosest particles that form some of the largest pores in soil. Silica, that sand is made of, some of you might be familiar with it as also the material that makes glass. Clay, on the other hand, are actually the smallest particles in the soil, and those are composed of minerals that are aluminosilicate sheet structures. These sheets can be arranged in a 1-to-1 ratio, so a 1 silica sheet with 1 aluminum sheet, and those form what we call 1-to-1 clays. There can be 2-to-1 clays, which is 2 silica sheets and 1 alumina sheet. And really, this proportion of the sheets also determines the number of negative charges that are exposed at the surface of clay particles. And as we'll see in a couple of next slides, those negative charges are really important because they provide what is called a cation exchange capacity to the soils, and that's important for the nutrient holding capacity of the soil as well. So we can go to the next slide. So as soil scientists, how do we determine what kind of soils we are dealing with? What is the percent of the different particles in there, which in turn dictates their pore sizes and their capacity to support life. We use this triangle called the soil textural triangle, and it has 3 sides. Each side represents percent respectively of clay, silt, and sand. And so, for example, if there was a, can I use the pointer on this, or mouse? So for example, if we were looking at a soil that had 21% clay, which would fall somewhere here, and we drop a line straight down, so I'm getting a signal that we might be running out of time, so I won't do a demo of the soil textural triangle, but what it really shows us is that looking at the percent of clay, silt, and sand, we can classify soils into different categories, such as clay, sandy clay, clay loam, etc. And each of these categories have specific properties that help us then determine the best use of those lands as well. We go to the next slide. So with that, those were the mineral fractions of soil, and the other important part that a majority of our presenters will also be talking about today, which is soil organic matter. Soil organic matter, which is complex with the mineral fraction of the soil, is really important, and it provides basically food for soil microbial organisms. It has the capacity to hold water in the soil, which again is important for all the life forms in soil. The complexation of soil minerals and organic matter provides shelter for the microorganisms and small organisms that live in the soil by forming those three-dimensional spaces that I was talking about. And of course, those pore spaces also allow for an oxygen exchange and air exchange. So all in all, making soil a habitat which can support a really, really large diversity of organisms. In fact, soil is the most diverse ecosystem on our planet, and a teaspoon of soil can have tens of thousands of different types of bacteria living in them. So what is soil organic matter? And as we know that from the word organic, it comes from living organisms. And it has long been known that different types of plant materials, when they degrade and go through different stages of degradation through microbial action in the soil, they can form certain fractions which can be stabilized in the form of organic matter in the soil. So we have a table here showing how lignin is converted into different types of organic matter, humic substances in the soil. And I do want to say that this is a part of the earlier research. However, soil organic matter and its composition is a very active area of research. And as we're studying it more and more, we're finding out that soil microorganisms and their debris and their dead bodies also have a really, really important role in forming some of the resilient fractions of organic matter that we didn't know about earlier. So all of those different types of life forms that are supported by soil are really important in forming soil organic matter, which is the stable carbon fraction in the soil. You can go to the next slide. So there is another way that we can classify or characterize soil organic matter, and that is through the chemical properties of the different components that form organic matter: fulvic acid, humic acid, and humin. And really the takeaway point here from this slide is, as you can see, these different fractions of organic matter either increase in the degree of polymerization in molecular weight and carbon content. And as that happens, those fractions that are more polymerized, that are heavier, they are harder to degrade, they're much more resilient to biodegradation, and that's really the form of carbon that's more resilient in the soil. And carbon that can be stored in resilient forms within the soil that is coming from life forms is essentially the carbon that is not entering our atmosphere as carbon dioxide after oxidation. So what that really makes soil is a great sink for carbon in the soil. That atmospheric carbon dioxide, when it is photosynthesized by plants and undergoes all of these microbial transformations and becomes stable carbon in the soil, it is essentially being sequestered in the soil, and that really gives soils the ability to help manage our climate change as well as atmospheric carbon dioxide concentrations through proper management. So we can go to the next slide. And once again, looking at soil organic matter, very complex structure here. We'll not get into the details, but again, the takeaway here is that it is a really complex structure, so it's resilient to degradation. It is more stable in the soil. And as you can see, there are lots of different functional groups. Organic matter does have the ability to complex with different types of nutrient ions, similar to clays, such as magnesium or other positively charged ions that are plant nutrients. Its structure is such that it can be hygroscopic in nature or complex with water molecules, and therefore increase the water retention capacity of soils as well. So as we mentioned, soil organic matter does have multiple benefits, including water retention. It can provide it can hold up to 20 times its weight in water, and therefore increase the water retention capacity of any soil that it is incorporated in. So as we kind of continue to talk about all of these important benefits of soil organic matter, these have been widely recognized by the research community for decades now. And using some of that information, USDA and NRCS has also outlined some steps to promote soil health. And what these steps really are about soil health are different ways of managing the soil that can retain organic matter in the soil. So how can we do that? We can do that by disturbing the soil as less as possible. So we expose less of the organic matter for oxidation. We can increase the diversity of soil microorganisms, and having those increasingly diverse microbial communities also provides a much more resilient biological community in the soil that can help maintain that soil health and organic matter. Keeping living roots growing throughout the year. We all know the importance of roots in formation of this organic matter and keeping it in the soil. So we maintain those roots, we maintain soil health, and then also keeping the soil covered as much as possible. Again, decreasing or reducing the amount of oxidation of that organic matter from the soil. And once again, just kind of highlighting the benefit of those healthy soils that have that carbon. It can get us improved plant health and yields, increase water infiltration and retention, sequester atmospheric carbon dioxide, reducing sediment erosion and dust because it forms more stable aggregates, improving water and air quality, and also improving biodiversity. All of these benefits, go to the next slide. All of these benefits of soil organic matter as well as soil health have been talked about for many years now and were memorialized internationally by the United Nations in 2015, when 2015 was declared the International Year of Soils. It was highlighted on the UN website and in their materials as well that building this soil organic matter equates to carbon sequestration, like we talked about, and it can help us deal with so many issues across the board, such as waste management. So making compost and compost that can be then incorporated in the soil and increase that carbon out of our different waste streams helps us deal with waste management as well as our climate change issues. It also, adding in compost adds nutrients to the soil, so that helps us in increased crop production. We can also deal with a variety of different waste streams, not only municipal waste, but also agricultural waste and manure. Manure itself is a source of greenhouse gases, but composting that manure and putting that back in the soil can provide us with an avenue of building that carbon in the soils and carbon sequestration. And not only in agriculture, but in natural and working lands, healthy forest lands can provide wood and other forest products. Some of these other forest products can then again be reincorporated back into the soil. So there are many different mechanisms by which we can bring that carbon back into the soil, sequester that carbon, and enhance soil health. So also recognizing the importance of healthy soils, not just internationally, but within our state of California, CDFA launched the Healthy Soils Initiative now at this time almost a couple years ago. Governor Jerry Brown recognized how important soils are for our state. California is one of the largest agricultural producers in the nation, producing more than 400 different types of agricultural commodities, what we call specialty crops, fruits and vegetables, tree nuts, some of these crops that our state is a leader in producing. And it is really, really important to maintain the health of our soils, the fertility of our soils, to ensure these economic gains that we get from our agricultural production. and also for our food security. So once again, just highlighting that California leads the nation in 90 commodities, has over 75,000 farms. And one of the most important things here in California is that we have year-round production in some regions because of our wonderful climate. And therefore, it's really, really important, again, to name not only that California contributes to food security for our nation, but it's really important for us to keep our soils in good health to continue playing this role for us. So once again, just very quickly looking at the diversity of soils in California, a diversity of crops in California. This is a snapshot of Northern California. And if we go to the next slide, every different color on this map represents a different crop. So within even a very small region in Northern California, this is a snapshot of, I think, Butte County. And we're seeing so many different crops being grown. So if we look at across the state, across our entire productive land, just the diversity of crops being grown in this state is astounding. And once again, highlighting the importance of soil health, not just to maintain that crop diversity, but also we went through one of the longest droughts in recent times in the state. This is a snapshot from 2015 showing large part of California's production land in drought. And we talked about how organic matter and soil health and enhancing soil health can increase water holding capacity of the soils. It has the potential to make us more resilient over time into facing these type of droughts, or as some of the climate scientists have predicted that the wet-dry cycles might get more intense in the future. We really have to think about how to keep our soils and our agriculture resilient. Building soil organic matter can be a key to that as well. So our next slide, that's another snapshot from 2013 showing how much the snowpack had decreased to 2014 and how much our rivers had reduced. So once again, remembering that drought and remembering how soils can play an important part here. Go to the next slide. So with all of that in mind, as part of the California Healthy Soils Initiative, CDFA launched the Healthy Soils Incentive Program in 2017. This program is housed under the Office of Environmental Farming and Innovation at CDFA, and the program is funded through California Cap-and-Trade Funds or the Greenhouse Gas Reduction Fund. We will be talking much more in detail about this incentive program in one of our other presentations. Dr. Chen from CDFA will be presenting this topic, so I will not take a lot of time. But we would like you to remember that, the next slide, for any of our programs to be successful and for us to be thinking holistically about soil health in California, strong partnerships are needed, not only between CDFA and the farmers, but also engaging with academic and nonprofit organizations, making sure that our research and science are always informing these type of programs, and then how to make those programs and research more accessible to farmers to use, how to engage public and important stakeholders into constantly informing those programs so that we can improve them and we can build together towards a future full of healthy soils. So with that, I would like to thank you all for your attention, and we can probably move on to the next. Thank you.
Thank you, Dr. Joshi, for the wonderful introduction to the importance of soils. We will go on to the next session, our panel number 2. And panel number 2 is titled Examining the Impacts of Soil Degradation in California and Around the World. And we will begin by having Dr. Elia Scudiero talk about his work. And Dr. Scudiero currently serves as a postdoctoral research fellow at the University of California, Riverside in Environmental Sciences. He also works in the USDA ARS US Salinity Laboratory. His main research interests include the use of geophysical measurements to characterize soil spatial variability and regional scale soil mapping. He's a graduate of the University of Padua in Italy and holds a Master of Science in Environmental Sciences and a PhD in Crop Sciences with a focus on environmental agronomy. Dr. Scudiero, we're going to turn it over to you now, and just say next slide to advance the slides, please. Thank you very much.
Thanks a lot for the introduction. So yeah, good morning. As I said, I'm Elia Scudiero, and I carry out my research at the USDA Salinity Laboratory in Riverside, California. Today I'm going to talk about some of the recent research I have carried out with Todd Skaggs and Dennis Corwin on mapping and monitoring soil degradation in California's agricultural soils. Next slide. So, as many of you may know, soil salinization is a threat to soil quality, and especially in semi-arid regions, such as the most of the California farmland. At the Salinity Lab, we aim to identify and understand the drivers and spatial patterns in agricultural soil salinity to support the development of mitigation strategies and management plans. And in particular, my research focuses on developing tools for assessing and characterizing the spatial temporal variability of agricultural soil salinity at various spatial scales. Soil salinity has many social and environmental impacts. It can limit agricultural productivity, threaten the long-term sustainability of soil use, increase risks of flooding, be a hazard to human health and to wildlife, and can lead to increased soil erosion. Next slide. Soil salinity refers to the presence of soluble salts in the soil solution, and it's generally measured as the electrical conductivity of the saturated soil extract. This allows classifying soils into different classes, from non-saline to extremely saline, with most commercial crops not growing in the extremely saline range. Globally, almost 1 billion hectares of soils are salt affected, and what's most concerning is that 20% of the world's irrigated farmland is salt affected, and half of which is found in 4 countries: China, India, Pakistan, and the United States of America. Here in the US, major salinity issues are found in the Central Valley of California, and most of the salt affected soils are found in the southern part of the Central Valley, in particular in the western part of the San Joaquin Valley. So let's take a closer look at the western side of the Fresno County for a practical example. Next slide, please. So the soils of the western Fresno County are rich in soluble salts coming from the alluvium originated in the Diablo Range. Most of the salinity problems are found in proximity of the Kings and San Joaquin rivers because of the shallow water tables in those areas. Agriculture has been possible in the last century in this area because of the use of good quality water coming from the Sierras. Because of irrigation from the 1940s to the 1990s, there was a general decrease of soil salinity in the first meter and a half of the soil profile. Next slide, please. So this change is evident when comparing a soil survey from circa 1945 on the left to the NRCS data from the early 90s on the right. In 5 decades, most of the strongly saline areas of western Fresno County were changed to slightly and moderately saline, whereas most of the areas characterized by non-saline soils in the 40s were still non-saline in the 90s. Next slide, please. Because salinization in this region is tightly connected to agricultural water management, it is important to study and understand the implication of reduced water availability on soil quality. Recently, as previously said in the previous presentation, California underwent a historical multi-year drought. During this drought, the water allocation to farmers in this area were drastically reduced. So some farmers resorted on using saline groundwater for irrigation, but the use of such water likely increased soil salinity, decreased soil permeability, and increased the rate of land subsidence, which is a serious issue in the Central Valley. On the other hand, and that's what we're going to focus on today, where irrigation with groundwater was not feasible, farmland was fallowed. Before the drought, less than 12% of agricultural soils in the western San Joaquin Valley were fallow, whereas in 2015, the percentage of fallow land went up to 33.7%. In the next slides, I will talk about salinity changes over areas characterized by shallow water table and undergoing this land use change from irrigated land to fallow land. Next slide. So first, let's take a look at a field scale study. Here we have a site that is 32.4 hectares, and it's saline and sodic. It's a saline and sodic field, and it's characterized by shallow water table. So an experiment was carried out here, and it was about the use of lower quality water for irrigation of marginal land. And the site was before that originally fallow. And in the year 2000, irrigation started, and the field was cropped with a salt-tolerant Bermuda grass for forage. So irrigation was carried out for 10 years at the site. Then the drought started and irrigation stopped. During this time, salinity was measured at 5 time points at different depths over 40 representative locations. In particular, these locations were selected using the apparent electrical conductivity directed soil sampling methodology, which was developed here at the US Salinity Lab in the past 30 years by Dennis Corwin and colleagues. Next slide, please. So the experiment indicated that drainage water could be used to reclaim non-productive saline sodic soils, bringing them into agricultural production. And this is clearly visible from the first 3 pictures in the slide. However, and this is most important for us today, when irrigation terminated in 2010 and 2011 because of water shortage, the field quickly returned to its original saline sodic conditions. The figure on the right shows how the salinity levels in the root zone were slowly decreasing between 2000 to 2009 thanks to irrigation, but in less than 2 years, they returned to the original or higher levels because of upward movements of salt from the shallow saline water table. Next slide. So to properly manage soils in the Western San Joaquin Valley and assure long-term sustainability of their use, it is important to understand the spatial temporal dynamics of soil salinity trends, especially in scenarios with uncertain water availability. At the field scale, sensor measurements and soil sampling can be used to monitor salinity changes in an expedite and economical manner. However, such approach would be unpractical when working at broader scales, that is, when monitoring salinity changes over thousands of fields at a time. Next slide, please. So in recent years, our research at the Salinity Lab has focused on the use of satellite data to map a root zone soil salinity. In particular, we developed a modeling approach that estimates salinity from multiple year canopy reflectance data, meteorological information, and land use information. This approach provides accurate and reliable estimation of root zone soil salinity. In particular, the model for the Western San Joaquin Valley has been thoroughly validated using independent sampling, spatial cross-validation, expert-based quality assessment, and by positive feedbacks from the farmers and the landowners that we collaborate with. In the past 4 years, we published extensively on this topic, and I'm reporting details on on the studies that we've done here in the slide, and you can read on these papers about the model formulation, calibration, and validation. So feel free to contact me if you want to hear more about this. Next slide. So clearly, the major benefits of using remote sensing is that we can map salinity over very large areas at a fairly high spatial resolution. Here, I'm showing the salinity map that we made for the 0 to 1.2 meter soil profile in the agricultural soils of the Western San Joaquin Valley with a resolution of 30 by 30 meters. By using this remote sensing approach, federal or state agencies can monitor soil salinity changes over a large areas in the mid-long term, say every 10 years or so. So let's now take a look at the farmland in the former Broadview Water District for an example of the information that could be generated by a mid to long-term salinity monitoring program. Next slide, please. The Broadview Water District is no longer an active district, but it comprised of 2,400 hectares of farmland in Fresno County. It sat next to the San Joaquin River and was characterized by shallow water table. In the 1940s, this land was strongly saline, but then after 50 years of irrigation, it was mostly slightly and moderately saline in the 1990s. it was a very highly productive farmland with average yields that were in the top percentiles for the entire Fresno County. The land was irrigated until 2006 and then became fallow as water rights were sold. And at this time, the water district was incorporated into a bigger water district. Next slide. So here I'm showing two maps. The top one refers to actual salinity measurements done in 1991 by Corwin and colleagues. The bottom one depicts the 2013 remote sensing estimations that we made. In 2 decades, field average salinity increased by 43%. Land that was originally strongly and extremely saline remained in the original state, but what's most remarkable is that soils that were non-saline and slightly saline in 1991 were characterized by an average increase of soil salinity of 97%. Practically, all the non-saline and slightly saline soils in 1991 had become moderately and strongly saline in 2014. So this is a clear example of relatively fast changes of soil quality over large areas that are due to land use change. Next slide, please. So to conclude, water availability induced changes in farmland management can lead to substantial impairment of soil quality in relatively short times. And at the regional scale, temporal analysis of crop remote sensing is a viable approach to monitor long-term soil salinity changes. Next slide. Next slide, please. So future research on this topic are, future challenges on this topic are to improve the modeling to support the prediction of salinity changes over shorter time spans, and to expand the modeling to wider extents. So we are working, and we would like to work in the future on expanding our remote sensing modeling to state, continental, and even global scales. Next slide. With this, done. And thank you very much for your attention. And please feel free to contact me at elia.scudiero@ars.usda.gov if you have further questions about our research. Thanks very much.
Thank you, Dr. Scudiero. That was excellent, and we look forward to partnering with you on future collaborations. We're going to move on to the next panel, because we were expecting to hear from Mr. Ronald Vargas from the Food and Ag Organization. However, he's not able to join us today, so we're going to move on to the next panel, which is panel 3, and it's titled Improving Soil Health. And this presentation was expected to be given by Dr. Guihua Chen here at the California Department of Food and Ag. However, she's unable to do this as we are working on the Healthy Soils Week activities and has been called to assist on that front. So I'm going to give this presentation for her. Again, my name is Amrit Gunasekara, and I'm Science Advisor here to the Secretary. I also manage the Office of Environmental Farming and Innovation, under which the California Healthy Soils Program exists. So as background, there was a Healthy Soils initiative that we started in 2015, which was the International Year of the Soils. And as part of that, we said we were going to focus on 2 things: the Healthy Soils program, that there's demonstration and incentive projects that will be financially incentivized to growers. So in this presentation, I will talk about this program, how it's designed, and also what the current status of the 2017 Healthy Soils program is, because we're just releasing some awards on some projects today. So next slide, please. When we started discussing the Healthy Soils Initiative in 2015, as a result of the International Year of the Soils, we looked to see what topics Healthy Soils can contribute to. And we realized we could not only build soil organic matter and sequester carbon, as Dr. Joshi noted, but there's other improvements too. It could have improved water quality from reduced sediment erosion. It could have greater water retention, as Dr. Joshi noted, in terms of drought mitigation. And when we started talking to the other agencies in this state, we found a tremendous lot of interest. For example, the Water Board was very interested in improved water quality as a result of building the organic matter content, which would then reduce sediment erosion. And so we have the Healthy Soils Initiative, next slide please, really identified some interagency actions that each department can take and run with. And one of the actions was to identify sustainable and integrated financing opportunities to facilitate healthy soils, as identified in action number 2 here. This was something that CDFA, the California Department of Food and Agriculture, and Secretary Ross had committed to working towards. In 2016, we received $7.5 million from the Greenhouse Gas Reduction Fund to support this Healthy Soils Incentive Program. And it was implemented through the Environmental Farming Act Science Advisory Panel, which is really the public forum where we are able to present the framework for this program and obtain public comment, and then work towards integrating those public comments into the framework. Next slide, please. The objectives of the program is really to build soil organic matter and reduce atmospheric greenhouse gases. This is the first Healthy Soils program that we know of that has used management practices to tie those management practices into greenhouse gas reductions and highlight the importance of carbon sequestration. There are very similar programs like this at the federal level, but they have not tied into greenhouse gas reductions to date. The Healthy Soils program, there was a funding distribution here. It was a set funding distribution covering a total of 17 management practices. These management practices have already been identified by the USDA and RCS as practices that can contribute to improving soil health. We had both the incentive program and the demonstration program, and I'll go into more detail on what those programs are in the next few slides. Next slide, please. So let me get started by talking about the Healthy Soils program itself. The Healthy Soils program, as I mentioned, covers 17 management practices. Here are 7 practices, and these practices look at building the soil organic matter below ground. This is below at the root zone level, and they include mulching. This is taking woody matter and mulching it up. As we know, that goes through the microbial degradation program, as Dr. Joshi noted, and then turns into soil organic matter, which is then a great carbon sequestration component. We also have residue and till management, and this includes no-till and reduced till. We know that the Great Depression was also facilitated by us overusing and tilling our soils, and so these are important practices that we're trying to encourage growers to adopt. We also have cover crops in there. We know cover crops, especially if you use legume cover crops, can not only increase carbon sequestration, but also help with nitrogen as well for food crop production. There was another practice, and this was compost application. We have 3 different practices in compost. This is compost application to annual crops, compost application to perennial orchard and vineyard crops, and compost application to grasslands. And compost application is part of a bigger effort to reduce food waste from landfills, move those food waste into compost facilities, and then also incentivize growers to take that compost and add it to their fields, because it's an incredible nutrient source and also a carbon sequestration source for our soils. Next slide, please. We can go on to some other above ground management practices, and there are 6 that are listed here. These include things like wind barriers, that if you plant trees, build the carbon in the trunks of the tree as lignin. We have field borders, filter strips, contour buffer strips, riparian herbaceous cover, and vegetative barriers. Next slide, please. And then we go on to the woody cover practices. These are 4 practices. This is establishing woody plants. As I mentioned, windbreaks, includes riparian forest buffers and hedgerows. And then for the grazing lands, there is silvopasture, which is the planting of trees in grazing lands. Next slide, please. Part of this program was to establish a quantification methodology. And we were asked by the legislature when we develop any of our greenhouse gas reduction programs to work with the Air Resources Board of California to develop a quantification methodology, which is essentially telling us how do we quantify the greenhouse gases that are part of this program. We work closely with USDA NRCS again, and they had a program called Comet Planner, which we worked with them to adapt for California systems in consideration of the soil profiles that exist in the different counties. It's a very easy to use tool. We were happy that it was adopted as a quantification methodology because it widely helps, it tremendously helps in the application process for growers. Next slide, please. If we look at Comet Planner, and here's a screenshot of it, we can simply see that it's an easy-to-use tool because you can just simply enter the amount of acres per practice that you're choosing to apply on your farm. And what it will do is it'll calculate a total carbon dioxide equivalent greenhouse gas reduction. Now, you can apply multiple practices on farms from the practices that we offer as part of our incentive program. Basically, they're allowing growers to look at their farm, see what best fits their farm, and make decisions based on those practices that they choose. Next slide, please. And then we also have here Comet Planner. These are for the compost practices. We had a year-long process to determine what compost rates this program could incentivize. There is no set agronomic rates for the different crops, but for our program, we had to set some rates, otherwise all our dollars would go towards compost addition if applicants asked for them, and we wanted to include other practices as well. So we set some rates, minimum rates and maximum rates that you could apply for our program. Growers are allowed to use more compost application rates than listed in our requirements, but this is a simple calculation that was also added to Comet Planner for compost. Next slide, please. We have a payment methodologies that I will talk about quickly. We have a flat rate payment system like the USDA and RCS practices. We have a maximum amount for the incentive programs of $50,000 that a grower can apply to. We also have a demonstration projects component. There are 2 different types of demonstration projects applicants could ask for. And this was really designed to facilitate public comment that was provided to us as part of the Environmental Farming Act Science Advisory Panel. So we had 2 types of projects. Type A projects was a maximum of $250,000. And these projects had to not only provide outreach to growers, but also collect some greenhouse gas data collection and do one of the practices that we are incentivizing. And projects type B was a maximum of $100,000, and that simply provide outreach activities. One thing we realize is with our 9 million irrigated crops in this state, and many different crop types, we are not able to move this money to all those acreage. So one of the reasons we set up demonstration projects is for growers and extension specialists to come into partnership, also nonprofits to come into partnerships to hold demonstration days and invite growers to come and learn further about these practices so that they can then take that information and try to apply it to our farms, to their farms. It's really an outreach component to move beyond the limited funding we have to really educate and help growers to see the benefits of healthy soils and building carbon in their soils. The program duration is 3 years for all the incentive projects. Next slide, please. We have an easy-to-use online application process. The application process goes through an administrative review, a technical review, and then there's unsuccessful applicants that are given feedback, and also an identification of successful applicants who get an award. And then that stimulates further grant agreement that's initiated following by an award notice. Next slide, please. We had multiple levels of review as part of the scoring. We had a breakdown in terms of project feasibility being one of the highest. We want to make sure that these projects are feasible in saying what they're going to do over a 3-year term. The next biggest scoring mechanism was the greenhouse gas reductions. And then we had also some other components such as project sustainability, conservation plans, disadvantaged community benefits, and several other soil health and environmental co-benefits. Let me now move on to the 2017 Healthy Soils Program status. This information on this next slide is brand new, and today we will be announcing as part of World Soils Day that we're going to award these projects, and we have a total of 64 projects totaling $1.77 million that we're awarding for the Healthy Soils Incentive Program. And we're also going to award 22 projects totaling $3.46 million as part of the demonstration projects. You can see that all these projects had significant matching funds, which we were very pleased about. This information is now live on our Healthy Soils Program website. You can simply type in Healthy Soils Program into whichever browser you're using, along with CDFA, California Department of Food and Agriculture, and it'll take you to our website where you can see a brief summary of each of these projects and what we're trying to accomplish through funding of these projects. Next slide, please. We are also embarking on an effort to include other new management practices in the Healthy Soils Program going forward. We have a solicitation for proposals for folks who would like to see us consider new management practices, and this is open till December 18th. And you can simply send us your written comments in a letterhead stating what new management practices are. There is some requirements that you have to provide as part of this request. You have to provide the scientific aspects and suitability for these projects so that we have some scientific data to go off in evaluating these projects. We're going to have an interagency evaluation, and then pending the Environmental Farming Act, Science Advisory Panel meetings and discussions will develop quantification methodologies to accommodate those management practices. There is this public comment period I mentioned through November 6th to December 18th, and the next 3 practices which we hope to add as part of an agency addition is really focused about nitrogen and reduction of nitrous oxides. Next slide, please. We have received additional funding, or we have proposed to receive additional funding as part of SB 5. This was a Parks bond, and the $10 million has been allocated in this Parks bond for the Healthy Soils Program. Now, this Parks bond is up for voting by the citizens of California next June. So we will only find out if we receive these funds after June of 2018. With that, I'm going to provide this slide. Again, this presentation was done by Dr. Guihua Chen in coordination with Dr. Joshi. We are very pleased to be part of this effort and this week in hosting all the good things that are going into our soils and really highlighting the importance of food security through building soil organic matter, and also the importance of carbon sequestration and how soils can really contribute positively in a good way to increasing our soil carbon. Thank you. We will move on to our next presenter, and that is Gregoire James. And Gregoire James serves as president of Genera. And Mr. James founded the company in May of 2009. A little bit about Genera. It seeks to answer a simple question. Why do we have landfills? The vision of the company is to realize 100% landfill-free globe by 2040. The vision was developed out of the necessity to protect the survivability and longevity of our species due to the damaging factors landfills have on our bodies, years, land, and water. Mr. James, you can take it away, and please simply say next slide, and we'll move the slide along. Thank you for being with us today.
Hey, thank you very much, and thank you for your introduction. And it's been a quite exciting morning so far. It's one of the greatest presentations on soil I've seen in a long time. I'm not a scientist, but I'm more of an entrepreneur. I worked in corporate real estate actually for about 10 years, where I sold investment properties, office buildings, retail buildings, and I noticed a gap between waste and recycling in the commercial sector. And it was just really a simple curiosity about, where the gaps in waste and recycling were. And one of our first projects, which is why we were invited here today, was a worm composting project that we did in Toronto. It was a pilot project. We had a number of groups. Starbucks had joined us. Zipcars was one of our customers, and everyone was really excited about the project because it was the first time someone had mentioned to them and about soil and about food waste and how the two are connected. So next slide, please. This is a quote that really motivates me quite a bit. An ABC broadcaster, Paul Harvey, he's not with us any longer, but he once said that man, despite his artistic pretensions, his sophistications, and his many accomplishments, owes his existence to a 6-inch layer of topsoil and the fact that it rains. I mean, for me, that was very profound because, I think in the modern day society, we're very disconnected from soil. And I think one of the reasons why I created Genera. Genera is the Latin word for sorting. And so Genera is a sorting cycle. And we just help really with education and execution of programs and projects to try and connect people with waste and how that helps. Next slide, please. So we really have a challenge on our hands. Many international communities are discarding over 70% of their food waste and the food waste value. And what is really food waste value? I'll get into it very shortly. But with the circular economy on our doorstep, a transition to a more sustainable practice is absolutely necessary today. We're living in a really defining point in history where we will be judged for our actions in the future. And so we must not just be sustainable, but we must build a platform where accountability for our actions is automatic and also comes as second nature. And so the solution, I think, is, we really have to be connected to a goal and to a vision. And my vision is a landfill-free globe. But this vision must really offer a value proposition because we really live in an economy-first world. I mean, as much as we like to talk about sustainability and as much as we like to talk about helping the planet, the reality is that most times, unless there's an economic incentive, the environmental solution is not going to be worthy enough for people to adopt. So my big question is, can we have economic and environmental sustainability together? And so the vermicomposting project, which I began, was to really look at food waste. And the fact that it represents a considerable challenge, but in every challenge, as we know, lies an even greater and more significant opportunity to win. So vermicomposting represents this massive opportunity to relocate food loss value, increase crop yields, reduce fertilizer usage, as worm castings are a fertilizer. It also improves water absorption, which is huge for drought-ridden states such as the state of California. And the other thing is it really reduces waste hauling costs, because obviously when you're moving food waste, it's very water intensive, and moving that waste really is very expensive. So the intersection of these verticals really exceeds $1 trillion a year in unnecessary spending. Next slide, please. So I really didn't know anything about vermicomposting before I started, and I think it was really helpful because everything was new and everything was interesting to me. And I think when I first looked at food waste in general, I found that trucks were moving food, many miles away out of urban centers, and often they were dealing with food waste in ways that wasn't really environmentally friendly, almost very methane heavy processing, which we know, food waste causes methane, which is 21 times more detrimental to the environment than carbon is. Methane is the really big story. So I'll tell you a little bit about what we did, and it'll be on the next slide, please. So it was the closed-loop vermicompost recycling program. We actually started on bicycles, and the reason being is because we wanted to really say, well, why do we even need vehicles? I mean, the reality is we need vehicles because, again, food waste is heavy. We have to transport it many miles away. But what we did is we started just composting in an urban center. So we replicated a worm composting environment using optimal growing temperature, pressure, and humidity for worms, as well as pH, because acidity is not friendly to worms. And we replicated this environment in an urban center, and it was powered by bullfrog power, which is clean green energy, solar and wind. And we also actually even partnered up with a plant-based protein supplement to help our cyclists really, have a reduced impact. So it was a program which accepted 100% of all plant animal matter, including any of their byproducts. Many composting projects and programs today, have exceptions. Some say you can't put napkins in because it damages the machines, or coffee filters, or some say you can't take bones. But ours took 100% of everything that once grew on the planet. And this was important because these nutrients all really came from soil. And so what we created out of this process were worm castings. And worm castings really help with hydrating, ensuring that soils are hydrated. And it's also 10 times more nutrient dense than regular compost. And this program wasn't, it wasn't a huge success in the sense of, it wasn't adopted nationally or anything, but it really actually started to raise awareness. And I think awareness is where we have to start with soil. So next slide, please. So the big question we had was, what's the return on investment? And I know this isn't an investment seminar, but we want to touch on a couple points. Next slide, please. So what is the cost of all these cycles? What's the cost of food waste? What's the cost of fertilizer? Where all these costs come from? Well, really, they come out of our pockets because we pay for these produce items, and all these costs are factored in. So if we really eradicate food waste, the FAO is saying that food waste is exceeding, I think, $1 trillion annually, and it's almost $3 trillion if you incorporate all the social and environmental effects. But just really in a snapshot with regards to the USA, it's about a $300 billion loss every year with regards to food waste. The steaks go bad in our fridge, or we throw these these produce items away. But what we found was that there was a huge gap between waste and recycling again. So I mean, how many of us, I'm raising my hand, have access to ensuring that all our produce, all our food goes back to the soil? Not very many of us. We were recently contracted by a company who had 50,000 kilograms of oranges that they wanted to dispose of. And that was a huge amount. We're talking many truckloads of oranges. So we actually put them through our worm process, and we created worm castings. It was a huge win. But these oranges came from South Africa. They grew over many seasons to become mature, and they were going to be destined for landfill if we didn't step in. So I think we really need to focus on what's the cost versus benefit. Again, the other point is fertilizers. Worm castings are actually true fertilizers, and I'm sure many soil experts can attest to this, but they do help really in the overall nutrient supply for the growth. of products. And of course, lastly, cost of hauling. It's estimated that by 2022, it'd be about $1.3 trillion globally, the waste industry. But a lot of the times we're wasting our time hauling food waste because there are ways of actually managing it within the cities. And one of the greatest things about using worms to process food waste is worms basically reduce the volume and weight of food waste by about 90%. And so what happens is there's a huge opportunity here to move less weight or to move less volume of things if we actually do worm composting more effectively and more frequently. Next slide, please. So, the question is, why now? When is the best time to plant a tree? Today or 20 years ago? I mean, that's the old saying, right? But so what's really going on our planet? I think the planet's in real trouble. I'm not an alarmist. I wouldn't necessarily call myself an environmentalist. I just try to find economic purpose for the environment, because I think that's why we're really missing all these gaps here. And we're currently in a soil emergency, as was stated by the United Nations in the Year of the Soils. I think it was 2015. If we continue our current use of soil, by 2050, so by 2050, our soil could vanish by about 3/4 from levels from 1960. So that's huge. And in fact, the United Nations also goes on to say that within 60 years, that our topsoil could actually completely vanish. So this picture doesn't really depict soil, but what it does depict is the fact that we have waste in our environment, and waste in our environment is actually going into our soil. There's traces of plastics now. As we all know, there's plastic in our oceans. Plastic is moving into our food chain, and we obviously landfill a lot of these products. A lot of groundwater is affected by waste. It's maybe one of those forgotten things, but I think it's very important. So what can we do? Next slide, please. So there's kind of three things we can do. Reducing food waste reduces operation costs, provides a new potential revenue stream, and also saves the environment. We have to remember that when we throw food away, it causes dangerous greenhouse gases, and nutrients simply do not return to the soil. That's huge. If there's one takeaway today, it's that we have to replenish nutrients into our soil. And there are ways commercially to do it, but it's not the way that the planet works. For 2 million years, the soil has been on our planet. It's been doing it in a very organic way. The other real pillar, of course, is revenue. Value could be diverted. Value can be derived from food waste, and it also can be realized. And lastly, carbon. It's been mentioned today. Here's a fact, by the FAO, that the amount of uneaten food every year produces 3.3 gigatons of CO2 annually. And to provide a sense of scale, an A380, which is one of the largest passenger aircraft in the world, it would have to fly nonstop for 13,698 years to emit the same amount of CO2 that uneaten food emits in one single year. And that's like, it's such a big number we can't even comprehend. Next slide, please. So everyone's talking about the circular economy. What is the circular economy? Well, it's kind of like the new recycling. Just to touch on it very briefly, it's important for soil because, food waste, food growth, development farming is really, the original circular economy. Trees would grow, we would pick food off the trees would eventually die, would return the humus into the soil, and so goes the life cycle. And so the circular economy is something that the world is starting to adopt fairly slowly. It's basically to look at the entire value chain. Next slide, please. But before we actually talk about the circular economy, we have to make sure, and I'm not going to go into the slide, it's available for review later, but we have to look at all the pillars of what touches food and food waste. There's a value chain. There's the transportation, there's the farming, there's the grocery stores, and unfortunately, the only way that we could solve this is that we all collaborate. So everyone in the value chain has to collaborate with each other and recognize that soil is under intense pressure, and it's something that we all have to really focus on. So, but if you look at discovery of gaps, gaps within infrastructure, gaps between operations, why should a grocery store care about soil? Well, their business depends on it, really. But again, they're detached from it, so they don't really know. Again, we have to really focus on the economic incentives and try and really get everyone to collaborate. Hopefully, as new policies come on stream with landfill bans, that will be maybe down the road. Next slide, please. So where can we start? Well, I always say we have to start by starting. Next slide, please. So this is a slide that we developed, to raise education and awareness. Please go through it after. It's just a quick snippet of some things that we can do to become more aware of food waste, become more aware of our consumption. And it's very, very important that we all do some of these things. And you know what? The environment is a hot topic today. Hopefully, over the next 50, 100, or 200 years, hopefully we all get on board to really do things for the planet. Next slide, please. So people always ask me, what is a landfill-free globe? Do you really think you can get there by 2040? And I say, you know what? If everybody focused on the environment for just a week, we could get there by the end of the week. So, I mean, I'd like to share just my thoughts on, why I think we should be focusing on the environment. We should just all be conscious of, consuming less, eating less, just focusing on the necessities. I mean, obviously, we're not in a bad economic condition in North America, but around the world, there are a lot of people that don't have access to all the things that we do. So let's just be cognizant of when we consume. Next slide, please. So just a quick story of how we started. We started in 2009. One of the first bicycle projects that we did. We logged 9,700 miles on a bicycle. It's four times from LA to New York. We serve companies, municipalities, and we've also, even doing a project right now in research for the National Academies of Science, where we're focusing on, waste in the airline industry. So I think people are becoming more aware. This is just a case study of what we did for Starbucks. We looked at their waste, we studied it in groups, and we really identified food waste represented, greater than 50% of waste. So there's a huge opportunity there. Next slide, please. Again, just a little bit to summarize who we are. One of the things that I'm really excited about is about technology. We recently signed on with IBM as our tech partner. They're going to provide all the technology necessary for integration of our programs for not only our customers, but we're hoping to develop platforms that everybody can use. IBM Watson is an artificial intelligence platform, and it could help really change and reduce food waste. Next slide, please. So, in closing, I always share this thought and comment with everyone I talk to, and I always say it's time we stop just using the environment as a tool for the economy, and that we begin to use the economy as a tool for the environment. And I really want to hammer that home. The way that we can actually really help soil health is if we actually find ways of incentivizing people to enrich soils. And I think there are many, many ways. And obviously, we can't cover them all today, but I really appreciate having an opportunity to speak. Next slide, please. So I want to say thank you to all the participants in the panel today. Really excited again to hear all the comments, and what a great day, December 5th, World Soil Day. And yeah, thank you very much. Happy to answer any questions once the panel is complete. And thanks again.
Thank you, Mr. James. That was an excellent example of private efforts to build soil health and reduce food waste. We're going to move on to the next panel, which is about success stories. So we have gone through an introduction of what healthy soils is. We've examined potential impacts of soil degradation, and we've also heard on public and private efforts to build soil health. We're going to end with some success stories on a very positive note, because we need to keep this as positive as an issue as possible, with lots of potential to do a lot of good things. And we're going to start off with Mr. Glenn McGourty. Glenn McGourty is currently serving as interim county director and viticulture and plant science advisor for the University of California Cooperative Extension in Mendocino and Lake counties. His specialty is in plant science with a focus on horticultural crops, including wine grapes, vegetables, viticulture, nursery, and floriculture. He also works on landscape science and sustainable agriculture and weed science. He has a Master of Science degree in plant, soil, and water sciences from the University of Nevada, Reno. Glenn, can you hear us? And you can take it away?
Yes, I can hear you. Can you hear me?
Great. Yes, we can hear you great. And just send next and we'll move your slides. Thank you.
Okay, well, hello everybody. This is a really special day to be able to talk about soil health and the importance of it to our planet. And next slide, please. I think we all wonder about this. Is climate change inevitable, or can it be mitigated? And I think a lot of us feel frustrated that maybe our government isn't moving as quickly as we'd like to see. And I think in California, there's a lot of interest in this, especially in the wine industry, because there's a tremendous investment in matching wine grape cultivars to specific climates. And some of these climates, if they change, make it impossible for you to grow your fruit. I'm thinking of things like Pinot Noir and Chardonnay that need cooler climates, and warmth doesn't seem to be a problem, but we really worry about having a significant shift away from the climates we enjoy now. Next slide. I think it's been pretty well discussed today about how we're seeing carbon dioxide go up, and the other issue we don't talk much about, but deforestation is something that is also important and generates significant amounts of carbon dioxide. So agroforestry may be part of the solution for us, particularly in Northern California, where we have so many riparian areas and remnants of forests that are on our properties that we would like to keep, because essentially it also will fix carbon at a huge rate. Next slide. In the past, we always talked about soil quality, about what was good for the grapevine, and now I think the discussion is changing to soil health, and you've heard a lot about that today, even in these discussions. But soils also affect environmental quality based on how you use the land, and there's an opportunity for us to fix carbon in the soil, but there's more to it than that. Next slide. So we've heard this too. We're rethinking the role of farms in providing ecological services. You know, the watershed idea of protecting soil and waterways and storing soil, cleaning soil from excess nutrients. We certainly see beneficial insects and pollinators being affected by what we do on the farm. Habitat for diverse species and sequestering carbon. Next slide. There's a new idea out there called regenerative agricultural systems that seek to promote soil and plant health by using photosynthesis for the removal and retention of atmospheric carbon dioxide into stable soil carbon. And I think we're all familiar with that. Maybe we just haven't heard that name, regenerative agriculture, but that's becoming kind of popular, particularly with organic and biodynamic farmers. Next slide. The rhizosphere, of course, is one of the most important parts, where it's that interface of sort of the living and the inanimate, and it's a place where a lot of energy is stored in the form of carbon bonds, and virtually all nutrient assimilation by plants is affected by microbes, and feeding carbon helps the microbes. And essentially, what is the kind of the currency of a lot of these microbes is exudates from plants. So that's why it's really important to get living things into your system. Next slide. I'm not going to dwell on this other than just to say you can see microbes have huge amounts of biomass as we look down this list. I kind of outlined them. And you can see that there's some of the most important things that are living in the soil. Next slide. Go to the bottom line of this chart, and this is really important thing. When we look at conventionally farmed vineyards compared to organic, biodynamically farmed, or even sustainably farmed, we can see there's quite a bit more organic matter that gets pumped through the system, anywhere from about 1.2 to 3.5 tons of organic matter per year based on what kinds of cover crops you're growing, how much compost you're using, compared to about 3/4 of a ton in conventionally farmed systems. So there's quite a lot of room to absorb organic matter. When we're using compost, it's already been half digested and it's fairly stable, but it's expensive and energy intensive to move around. Next slide. So because there's such a high level of interest in this in the North Coast and the wine industry, a grant was put together through the California Department of Food and Ag Specialty Crop Grant, Block Grant Program. And we put one together that is called Climate Beneficial Vineyard Practices for the North Coast. The partners in this are the Natural Resource Conservation Service, all of the resource conservation districts in Napa, Mendocino, and Sonoma counties, and finally UC Cooperative Extension, and farmers. Next slide. So I think you've already heard this a little bit too from the NRCS. So going in the right direction, the things we know right off the bat if you want to preserve organic matter and improve soil health is keep the soil covered, minimize tillage and soil disturbance, try to plant diverse plant species to increase biotic diversity below ground. As I said, exudates from roots are the currency of microbes, and try to keep living roots in the soil as long as possible throughout the year. Next slide. So organic matter is very, very important, and cover crops are probably the cheapest and least expensive way to get organic matter into the soil. We have a wide range of cover crops. We've done a lot of research on that, and we have many, many different kinds that we can use. Compost would be next. Compost is a little more energy intensive, but it is a good way of recycling a lot of plant and animal waste, and we do a lot of that in our region. We're a net importer of compost in Mendocino County. We produce about 15,000 tons per year for 18,000 tons of vineyard, and we are 18,000 acres of vineyard, and we actually bring much more in. But almost virtually everybody uses cover crops in one form or another. And finally, conservation tillage to keep the organic matter in place. Next slide. I bring your attention to this. Here's another positive thing about using compost is if you look at the energy flow through a system when you're using chemical fertilizers, it takes a huge amount of energy to make them. They're usually made as sort of a byproduct to other parts of petrochemical manufacturing. However, if you're making compost and you're cycling nitrogen, it's a much more efficient way. So we figure in 1 ton of compost, we can get about 50 pounds of nitrogen per year per ton. So we're able to get most of the nitrogen that we need for a vineyard out of 1 ton of compost. Next slide. The important part of what we're trying to do with our grant is develop the whole idea of soil health assessment. So we're trying to teach growers about using cover crops and compost, but also assessing what's going on with their soil. And Cornell's done a really good job of this. If you want to see what a good soil health assessment program is, Cornell would be it. Next slide. So there's, next slide, please. So there's different tests. There's a physical test that look at the physical components, including texture, bulk density, and aggregate stability. Next slide. And then there's chemical testing, sort of the standard things we'd expect: pH, phosphorus, calcium, magnesium, and cation exchange capacity. Next slide. There's biological testing to take a look at total carbon, active carbon, total organic nitrogen, and potentially mineralized nitrogen in the soil. Next slide. So when you have all that information, then you're able to actually give an assessment as to whether your soil is healthy or not, and it's done really well. So you get kind of a scorecard from Cornell, and we're hoping to reproduce that for the West Coast, and we're starting to work with Oregon State University on it and their soils lab. There's also new techniques and products that are coming in terms of some of the tillage equipment we have that doesn't disturb the soil as much. It tends to kill weeds, but not necessarily invert soil, so it doesn't break the soil down as much, and it leaves organic matter on the surface. And you know, the growers have to get used to looking at this. Some people like very clean till look, and it doesn't look like that, but we stop weeds from growing. That's an important thing. And then leaving organic matter on the surface is a good idea because it also protects the soil from oxidizing organic matter, and it takes rain better. We have a lot of demonstration plots to show what things look like under cover cropping and different tillage systems. We're looking at mulching experiments, and we're finally coming up with carbon farm plans for people. So this is kind of how we're, you know, what we hope to do for the growers is come up with a way of giving them a guideline for how to fix carbon, and maybe sometime in the future we may be actually getting paid for carbon credits. Next slide. We've created the North Coast Soil Health Hub, which is resources for the growers to get together to look for information and to also communicate with each other. And it's online now, and you can find it by Googling North Coast Soil Health Hub, and it's housed by the Resource Conservation District in Mendocino County. Next slide. So what's the end game? Why are we doing all this? Well, first of all, it's a personal effort to address climate change that the growers themselves can do. The California Department of Food and Agriculture Healthy Soils Incentives Program may eventually start paying for carbon credits. And then it could also become criteria for certification, including the National Organic Program, the Demeter Farm Standards for Biodynamic, and other sustainable farming programs. So that's what we're hoping to do when this is all over. Next slide. So that's basically all I have to say. I think this is a very exciting time, and I think this is kind of a call to arms for growers to sort of take on their own management practices to help ease the release of carbon dioxide into the atmosphere, and maybe stick it back in the ground and plant material where it belongs, and hopefully preserve some of our climate conditions that are favorable for agriculture as we know it today. Thank you very much.
Thank you, Glenn. That was excellent, and I'm so glad you're part of this effort to increase our awareness of healthy soils. This issue is truly international, and we are next going to hear from Dr. Ravi Gopal Singh. And Dr. Singh currently serves as a cropping systems agronomist with the International Maize and Wheat Improvement Center in Mexico. He has played an integral role in a number of agricultural sustainability projects across the globe, including the modernization of sustainable agriculture, which is a joint effort with his organization and the Mexican government to improve productivity and sustainability of Mexican agriculture. Dr. Singh, can you hear us?
Yes, I can hear you. Thank you for your introduction.
Great, and it's all yours, Dr. Singh. Thank you for being on this webinar.
Thanks. It is often said that all the plants, humans, animals are biochemical photograph of the soil on which they grow, which means if we get our food from a healthy soil, we are healthy, and if we get our food from not healthy soil, then we are probably not. So for me, the soil health is very important for sustainability, and the soils are, as we know, source of the nutrients for everybody on this earth. I'm going to make a small presentation on Mexican agriculture soil health and how our project Masagro is helping farmers to improve their soil and their sustainability. As you can see in this picture, the Mexican agriculture can be divided into two big halves. One is commercial agriculture, where farmers are using a lot of inputs, fertilizers, tractors, and on the other hand, we have subsistence agriculture, where farmers are using land races to produce their food at subsistence level. Next, please. Next, please. And so this subsistence agriculture systems, which is we call autoconsumer here, is dominated by monocropping and soil erosion. Farmers use land races and with limited use of external inputs, fertilizer, etc., etc. The biggest problem that the agriculture in Mexico is facing is soil erosion, and about 12 million hectare land out of 14 million hectare total agricultural land in Mexico is affected by erosion on one way or another way. So under these auto-consumer ecologies, farmers grow one crop per year, and they suffer a lot of abiotic stress because of soil health, degrading soil health, and not much efforts are being done to improve the soil quality under these kind of ecology, which is about 7 million hectare in Mexico per se. Next, please. So here is a typical example from south part of Mexico, from Chiapas, a monocultivo, monocropped maize systems on a slopy landscape without any erosion control method. Farmers harvesting 1 to 1.2 tons of maize every year, one crop of maize every year, a lot of soil health related issues, including diseases, abiotic stresses, etc., etc. Next, please. On the other hand, in north and central part of Mexico, we have commercial agricultural system where also farmers grow monocropping, often wheat or beans or maize or corn with a lot of external input. And now there are agencies selling a lot of fertilizers and biological products to improve productivity, but this is not helping a lot in terms of improving soil health. Next, please. And this is an example from South Mexico, Chiapas, where corn is taken twice per year over years, and which is affecting the soil health drastically, and they have again issues of soil-borne diseases in this particular ecology. Next, please. From northwestern part of Mexico, not far away from California, in Baja California, monocropping of wheat has led to serious problems of diseases, fusarium and Phalaris minor, a weed infestation, and several other problems related to salinity in this part of Mexico. Next, please. And also in the state of Sonora, one of the most important agricultural landscape in Mexico. This is a presentation of how soils are being degraded. In 1945, average organic matter content of this valley were about 200,000 hectares of wheat planted every year. Organic matter was 2.2%, which has reduced to 1% now. And the farmers are using more and more nitrogen every year. As you can see, the average nitrogen use in 1945 was 40 units per hectare, and Today, it is something 250 units per hectare in order to get similar yield levels. So the soil health is affecting, the hydraulic conductivity is reducing, organic matter is reducing, and farmers need to put more nutrient, which means reducing factor productivity of the soils. Next, please. In order to address those issues, we have our research program in 3 major locations here in Mexico City, in Batan, which is a semi-arid highland, and in Toluca, which is a subhumid, humid highland, and Ciudad de Obregón in state of Sonora, which is an arid but irrigated wheat-based production systems. Next, please. And one of the most important crop management strategies that we are using for sustainable intensification of production systems in Mexico is based on conservation agriculture crop management, which includes retention of residues, minimum movement of soil, and crop diversification, which is also very common in America. Next, please. So what we have found, for example, in highlands, in semi-arid ecology, if we put reduced tillage with some residue, we get higher stable yields. For example, the yield without residue, as you can see, in good years is about 5.6 tons per hectare, but in bad years, it's 3.6 tons per hectare. Whereas with residue, it's 7.8 tons per hectare in good years and 7.4 tons per hectare in drier years, which means the stable crop yields. Next, please. And also it comes with a good quality of soil. Similarly, in irrigated ecologies in northwest part of Mexico, our long-term experiments suggest that the permanent beds, which is reduced tillage and keeping some residue, can give higher yield over years, especially during dry years or years unfavorable for growing crops. Next, please. And in order to disseminate these kind of technologies, which is conservation agriculture-based crop management and using appropriate crop varieties, fertility, and GIS techniques, we use a model which we call hub model. And in this model, we use an experimental platform to do basic research together with technicians and researchers, and then we take the potential solution to the farmer's field in extension modules. And then from here, can I have the marker? Yeah. So we use the modules wherein we together with farmers and technicians, we use testing technologies, and then if some technology is found suitable, it is taken to a larger area, which we call area of extension, and then from there to area of impact by further larger adoption of potential technologies in a given ecology. Next, please. So here is an example. What are the different technologies in different states that are being demonstrated by this project? For example, you can see all yellow are the conservation agriculture-based crop management, and similarly other techniques of nitrogen, nutrient management, etc., etc. Next, please. This is one intervention that we are doing in northwest part of Mexico in Sonora Valley, where farmers are trying rotating their monocropped wheat systems with soya under conservation agriculture-based crop management. Next, please. In Sinaloa, which is also in the northwest part of Mexico, it's an ecology where farmers use monocropping of corn, and they use very high inputs. And our technicians and the collaborators, they are trying to demonstrate that with the use of sensors, they can drastically reduce their nutrient use. For example, in this case, the crop with 240 units of nitrogen looks as good as a crop with 150 units of nitrogen. Next, please. Again, in rain-fed ecologies, a highland rain-fed, high rainfall ecologies, there's an example you can see here. On the right, conservation agriculture-based crop management. On the left is conventional management system, and there after a heavy rainfall event, there's the inundation and waterlogging in conventional system, whereas in conservation agriculture based managed plots, the water movement is better and less inundation. Next, please. And so in Masagro, we have about 150 partners working together with 38 platforms on 120 hectares and 630 modules where we are demonstrating these kind of technologies and the large area of extension, conducting a lot of training, 371 farmers training, 52 trainers training. We have also a smart mechanization program where we are trying to demonstrate multi-use machines in order to achieve sustainability. And this kind of this project has especially been adopted by about 1.2 million hectare with 300,000 farmers in 390 communities. Next, please. So the farmers are being 300,000 farmers are associated with the project. There is 20% increase in yield in maize, 2% increase in wheat. Profitability has increased up for about 19% for maize farmers and 5% for the wheat farmers, and significantly reduction in cost of production and improved soil health have been observed in almost all the locations. Next, please. Thank you very much. Thanks for your interest.
Thank you, Dr. Singh. Thank you for joining this webinar. That was very, very interesting. And, you know, the link of building soil organic matter and increased yields is something that is very, very important and continues to need to be highlighted. So thank you very much. I would like to thank all the speakers for being on this webinar and taking the time off their busy schedules to share information on how they are participating in healthy soils and really working at all levels, the ground level and at policy levels, to move this discussion forward. We look forward to collaborating with you all in the future. We have a very open, collaborative relationship that's been established and encouraged through Secretary Ross at the California Department of Food and Agriculture. I'm pleased to say we had over 140 participants on this webinar. It's quite impressive how much interest there is in healthy soils, especially in this week and memorializing today's World Soils Day. We are not going to be able to facilitate questions. We have tried this before and it hasn't quite worked out well. So what we're asking folks to do is to please email us your questions and we will then start a string of responses to the speakers and to those asking questions to share that information. The presentations will be online on our website. You can simply type in CDFA, which stands for California Department of Food and Agriculture, and Climate Smart Agriculture, and it'll take you to a web page that has all our previous webinars, including this one, and we will have all the presentations uploaded including the contact information of the speakers so you can reach out directly to them if needed to be. Thank you again for being part of this webinar. We look forward to collaborating with you all, and we will sign off now from CDFA. Thank you. Bye-bye.